So in part A, we need to use base B, precision K, idealized chop-in floating point arithmetic to show that f of g of 1.015 is inaccurate where g of x is given. In part B, we need to derive the second-order quadratic Taylor polynomial approximation for f of x equals x to the power of 1 over 4, expanded about a equals 1, and we need to use it to get an accurate approximation to g of x in part A. And in part C, we need to verify that our approximation part B is more accurate. So let's start with part A. We will calculate g of 1.015. So part A, g of 1.015 equals 1.015 to the power of 1 over 4 minus 1 over 1.015 minus 1. It equals 0.248605929. So this is the exact value of g of x. In the ideal situation of chop-in floating point arithmetic, the operations are performed one at a time and the results are chopped after each operation. So the floating point number of the result with precision k equals 4 is f of g of 1.015 equals wait, let me write it from the let me write it a bit down here. So this equals f L of 1.015 to the power of 1 over 4 minus 1 over f L of 1.015 minus 1, and this equals 1.004 minus 1 over 0.015. Then this equals FL of 1.004 minus 1 over 0.015, and this equals FL of 0.004 over 0.015, and this equals 0.2667. So the absolute value of g of x is is right here. Yeah, I won't read it again. But the floating point value is 0.2667. So the machine precision for b equals 10 and k equals 4 is 1 over 2 times b to the power of 1 minus k, so it equals 1 over 2 times 10 to the power of 1 minus 4, so it's 5 times 10 to the power of negative 4. So the absolute error is equals the absolute value of FL of g of 1.015 minus g of 1.015 over the absolute value of g of 1.015, and this equals the absolute value of 0.2667 minus 0.248605929 over the absolute value of 0.248605929, and this equals 0.073. So it equals 7.3%, which is bigger, wait, let me move this a little bit, which is larger than 5 times 10 to the power of negative 4. So we can make the conclusion that f of g of 1.015 is inaccurate. Well, now let's do part B. So here's the Taylor's polynomial of order 2 of a function f of x around a point x equals a is f of x equals f of a plus f prime of a times x minus a plus the second order derivative of f of a over 2 factorial times x minus a squared. So we are given that f of x equals x to the power of 1 over 4. Then f prime of x equals 1 over 4 times x to the power of 3 over 4. And the second order derivative of f of x equals negative 3 over 16 x to the power of 7 over 4. Now we shall take an expansion around the point x equals 1, and we get that f of x equals x to the power of 1 over 4 equals 1 plus 1 over 4 times x minus 1 minus 3 over 32 times x minus 1 squared. Now approximate g of x by using the Taylor's polynomial f of x, and we get that fl of g of x equals fl of f of x minus 1 over x minus 1. So it equals fl of 1 plus 1 over 4 times x minus 1 minus 3 over 32 times x minus 1 squared minus 1 over x minus 1. And this equals fl of 1 over 4 times x minus 1 minus 3 over 32 times x minus 1 squared over x minus 1. So we substitute values and use idealized chopping floating point arithmetic here, and we get that fl of g of 1.015 equals fl of 1 over 4 times 1.015 minus 1 minus 3 over 32 times 1.015 minus 1 squared over 1.015 minus 1. So if we solve this, we get that this equals fl of 3 times 3.729 times 10 to the power of negative 3 over 0.015, and this equals 0.2486. So from part A, we have seen that the exact value of g of x is 0.248605929, and the absolute error should be less than 5 times 10 to the power of negative 4, and the error is within the machine precision here. So this result is much more accurate than the result in part B.